Assalamu alaikum everyone, and today we are going to be talking about redox reactions. Now, electrons are what make it possible to make bonds to form molecules, and when that happens, a lot of energy can be exchanged. But not all reactions on Earth involve electron transfer. As you recall in a few of my videos, acid-base reactions are more about swapping protons, but the most important reactions on Earth that happens involve the exchanging of electron from one molecule to another. Now, these are called redox reactions. Redox is a portmanteau of reduction, oxidation. Now hold on. What do these words mean? Okay, now let's think of it from a point of view. We all know what reduction is, right? It's to make less of something, and oxidation probably has something to do with oxygen. Well, in most cases those answers would be right, but in this case, no. Oxidation means the loss of electrons, and reduction, get this, means gain of electrons, which is exactly the opposite of what the word reduce means. Actually, I really wanted to punish the people who named them so inaccurately, but they didn't know any better and now they're all dead. Actually, the story behind it is that at that time, proto-chemists would make pure metals by smelting their ores. You know the kind. And they noticed that the substance would become lighter. So it's not really their fault and we can't really blame them. Actually, a French chemist named Antoine Lavoisier, the man who discovered carbon, oxygen, and silicon, figured out that this was because oxygen gas was leaving the compound, making it slightly lighter. Now, what he didn't know was the actual chemistry behind it. Oxygen is obviously and is the quintessential oxidizer. It pulls electrons off of molecules to make itself more stable. But if you heat it up enough, it gets all energetic. Nowadays, we know that redox reactions are about electron transfer. So you'd think we'll rename them, and some chemists have tried naming them electronation and de-electronation. But once a set of terms have been agreed upon, then it's really hard to change it. Now let's get to the reaction part. It's important to keep tabs on who has the most electrons and who has less. But atoms are fond of sharing electrons, forming covalent bonds. So this makes figuring things out much harder. We assign electrons 100% to the atoms that they are at the moment sharing them. So they are sharing them, but we pretend as though they're already in that atom. Now, the number that we assign is called the oxidation state, or the oxidation number. Now, don't get confused. We are aware that a covalent bond is happening and atoms are sharing it, but we pretend as though they're already splitting the atoms up. Now, to assign this oxidation number, we have a few set of rules. First, any element that is by itself will have an oxidation state or oxidation number of 0. So something like calcium or hydrogen 2 or sulfur 8, all elements have an oxidation number of 0. A monoatomic ion has an oxidation number as the charge of the ion. So Fe2 plus has oxidation number of 2, chloride has -1, and sodium ion has a +1 oxidation state. Number 3, oxygen will almost always be -2 unless it's in peroxides. And number 4, hydrogen will always be 1, and fluorine will always be -1. Now you can notice that we haven't assigned oxidation rules for many elements. This is because of this rule, that oxidation number of a molecule without charge will add up to 0. So think of something like SO4. We don't have to make a separate rule for sulfur. We can just do simple elementary algebra that I have said in my algebra video, so I don't even need to repeat it. So oxygen has -2. -2 times 4, that's -8. So sulfur has a oxidation number of +8, since they add up to 0. But it isn't always +8. That's why we don't have a rule for it. Now, you know the thing that I do. I always give examples, but there are a handful of redox reactions that I can go with. I mean, we have a lot of redox reactions here on Earth. Fun fact, the Statue of Liberty in the United States, you know, the blue statue, was actually orange, but after a few years the copper was oxidized and turned into blue. That's a redox reaction, oxidized. But let's put a simple one here. We have silver diamine, and we're reacting it with any aldehyde, and we're gonna add that up with a lot more, and we're gonna add that up with hydroxide to form carboxylic acid, water, and ammonia. So let's first determine the oxidation states. Now NH3 2 times will always be ±0, so we can ignore that. But silver diamine has a positive charge, so by that we can assume that silver has a +1 charge, because the silver diamine as a whole has an oxidation state of +1. Now aldehyde. The R here doesn't matter. It stands for it doesn't matter. There can be any group in here. All that matters is the CHO group. Now in the aldehyde, the oxidation state will add up to 0. So let's apply the rules. We know oxygen has an oxidation state of -2. Hydrogen has an oxidation state of +1. So carbon must have an oxidation state of +1. Now the hydroxide ion. We can put -2 and +1 just as it is. Now let's look at the product side. Silver, water, and ammonia and water doesn't change, obviously. Silver, now as it's lone and doesn't have any charge, will be 0. But the carboxylic acid here, we have +1, we have -2 and -2 oxygens. But the carbon now, according to the rules, will change to +3. So if we look at the whole reaction, silver was reduced from +1 to 0. So actually the reduction part, the word makes sense when you apply it in the charge. Phew! Silver was reduced and carbon was oxidized. Now the reduction half reaction is this. We have +1 electrons to neutralize it, and the products will be Ag plus 2NH3. And the oxidation part, as you can see, carbon is getting oxidized from +1 to +3, so we mark that. Now the overall redox reaction is when we combine them together, and we have to double the reduction half of the reaction to get the right number of electrons. Cancel the electrons, combine them together, and we get a perfectly balanced redox reaction. And if you actually apply this in a lab or something, then you will get pure silver out of it. As you can see in the equation, that we get pure silver out and the other waste products. So now we can go back to our videos about SN1 and SN2. I'll have them in the description, and then we can move on to elimination reactions, as we learned a whole lot about reactions. So that's all there is to it. If you want more videos about math and science, make sure to subscribe, leave a like down below, and comment if I made any mistakes or if I missed anything, or if you have any confusions whatsoever. Please let me know. And thank you for watching, and I will see you next time. Bye.